plane tickets. It's basically searching, and therefore this type of problem has to be. You have to make sure that the searching time should be less, should be as less as possible. Now here you already know that searching time, the maximum searching time for any algorithm is of order of n, and the minimum searching time is of order of log n. Okay, you already know that the big O complexity the complexity of any particular searching time algorithm will be between log of n to log of order of n. Obviously, order of n is not a good algorithm. Order of log of n of base 2 is the best algorithm. Anything in between is good, but our aim is that how to convert a searching algorithm to an order of log n. Till now, what you have read, you know that a linear search now you know that linear search is having an order of n, binary search is having an order of log n. Now you might say, if already I am having an algorithm of log n, why I need to do search any other algorithm? Because obviously you cannot find any algorithm better than log n. And already I am having the best algorithm, a binary search algorithm. Then what is the problem? Why I am going to find another algorithm? Because the fact, when I am going to perform an algorithm of log of n, you know that in a binary search, the array must be in a sorted order. Okay, it should be sorted order, and therefore you know that sorting will at least take an order of n log n time. Now you know that sorting will take at least n log n time, and that means when you are going to sort an array, it requires an order of n log n time, which is additional time over the searching algorithm. And therefore, binary search, once you sort it, it's okay, it will give you log n time. But if you are going to dynamically add elements to an array, or delete elements to an array every time you want to perform sorting, therefore the binary search algorithm independently might work in order of log n times, but actually it takes much more time than that, because you have to add order of n log n plus log n if the array is growing or shrinking and growing and shrinking dynamically, which is the case always. For example, once you are going to suppose a bank is opening account numbers daily, in that case it is going to the database will keep on growing every day. Somebody is going to close the account, again it will be having that it has to be the database has to be readjusted. And therefore the concept is that though I find that a binary search is the best algorithm, it is not the case if you are going to take the overall complexity, which also involves the pre-processing time to make that array. And therefore we have to find ways, a better way to maintain the algorithm. Now a binary search algorithm is one of them, though there are some problems in normal binary search algorithm, which we'll discuss, that what is the main problem with binary search algorithm. Okay, now let us take this algorithm BST. Now when you are performing a binary search algorithm, you have to make a binary search tree. when you're going to perform. That means I'm going to make a search tree, which is called a binary search tree. Why is it called binary search tree? Because there can be maximum of two children. Okay. Now the property is that, what is the property for a binary search tree? The root is bigger than what? The root is bigger than its left child and smaller than its right child. So this is the property of a binary search tree. The root is always bigger than its left child and smaller than its right child, and this definition will hold recursively. Recursively means at all levels. At all levels. This definition should hold at all levels. It means that if I have a tree like this, it might be say 90, 45, 40, 10, 42, and you see at 90 it is less than it is bigger than 45, it's smaller than 100. If you check at 45, you find you check at 45, you find 40 is now it's already having only the left child. That means 45 is bigger than 40. If you check at this point, you find 10 is smaller than 40 and 42 is bigger than 40. Now 40 is bigger than 10, smaller than 45. If you check at this point, you find that 95 is less than 100 and 150 is bigger than 100. It means that the property is not violated. But if I am going to put any number over here, which is maybe say 110, you will find that 110 is bigger than 95, and therefore this is not a binary search tree, though it is a binary tree. It's a binary tree, but it is not a binary search tree because this property is violated over here. If 110 would have been here, it should always been here. Because it is bigger than, smaller than 150, it should be on the left of 150. And therefore, this is not the correct position for 110. Now, if I come to this conclusion, you have to understand one very important concept, that every node is having its fixed designated position. Now, let us take an example. Let us take a value as, say, if I want to add a node which is having a value 65. Now, how will you going to do this? Now, in that case, what you are going to do with the 65, you have to compare starting from the root, because already you know that the root address is the only thing which you know. Now, if you are having one node, which is nothing but you are having a root. You start comparing 65 with 90. You find that 65 is less than 90, therefore you have to go on the left side. Now in that case, you go to the left side. Maybe you say it is 10. You might say it's called a 10. That means you say temp is equal to left of root or root of left. Now temp will come to 45. Now the algorithm what we have done previously is the same thing. You take a pointer temp which points to root. You compare the new value 65 with 90. If 65 is less than 90, you say temp is equal to root of left. If it is more than 90, you say temp is equal to root of right. In this case, temp will move to 45. Now again compare 45 with 65. You find that 65 is bigger than 45. Therefore, you have to go on the right side. Now, once you want to go on the right side, you find that it is null because here there is nothing. Here there is nothing. It is null. It means that that is the position which is vacant for 65. And what we are going to do is that you are going to put a 65 at this place. And it is very clear that you cannot have any other place for 65 than the one where I have written. That means all the elements, whatever you can get, will always have one and only one position. You have to find that position where I have to attach that node. Now suppose if I want to add a number, suppose as 125. What you are going to do? Again you start comparing with 90. It's bigger than 90. That will come to this one. Then you are going to again compare with 100. It is bigger than 100. Now 10 will come here. Again you find it is bigger than one. It is smaller than 150. Again move to the left hand side. You will find that I'll come here. Then you again compare with 110. You find it's bigger than 110. It means that it has to come on the right hand side. That means you have to find the place and it is here. It is there. Now the question is, how many times you have searched? Okay, you searched one time here. Now here you have searched it one time over here. Second time at this place. Third time at this place. And fourth time at this place. You compare 90 with 125, 100 with 125, 150 with 125, 110 with 125, and then you found that I have to put 125 in the right of 110. That means you search 4 times. For 65, you only search 2 times. One time with 90, other time with 45. Okay. Now in that case, what is the maximum times you can search? It depends on the height of the tree. It depends on the height of the tree. That means what I want to say is that the numbers which are coming depends on the height of the tree where you can attach a number. Now here, what is the maximum height of this tree? We start from here. H is equal to 1. H is equal to 2. H is equal to 3. The height of the tree is 4 because the first one is 1, then the second level is 2, 3 and 4. You take it anywhere. it is the height is 4. Till 125 were not entered, it is 4. That means this value is 4 is nothing but the height. And the maximum time you require to search is equal to the height of the tree. Now you start, you see, this is again the one, this is like this, is like this, like this. Because 10, 42 and 110 are at the same height. At the same height. Now how I calculate the height? The height is the maximum distance of that node from the root. The maximum distance of that node from the root. That means the height can be defined as the maximum distance of any node from its root. Now if you take 42, what is the height you can calculate over here? You will calculate from here. It will be from here 1, 2, 3, 4. 1, 2, 3, 4. You take from 95. It is 1, 2, and 3. You take this 110 again. 1, 2, 3, 4. And therefore height is defined as the maximum distance from the root to its children. That means if I take a particular, if I take like this, if I take a tree like this, and I want to calculate the height of the tree, for this you know it, for this one it is only h1, h2, h3, then you will come with this h4, h5, then you will keep on doing, then if you find for, let us take for this, 1, 2, 3, 4, 5, 6, 7, 8, 9, for this it is 9. Let's check for this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this it is 10. We check for this one 1, 2, 3, 4, 5, 6, 7. You calculate for only with a leaf.
Excuse me, sir. Sir, for height, we used to check from the leaf node, na, up to that node.
Because leaf node is at the highest, it is the last depth. No, therefore you just need to try to get it for the leaf only. For the intermediate nodes, not required, because intermediate node height will always be less than a leaf node.
Sir, I am asking about, we used to take, sir, we used to go from the leaf node up to the particular node for height, and for depth, sir, we used to come from root node to that particular node.
Oh, that is okay. But the only thing is that if you are going to calculate the height, the only reference you are having is at the root only. Therefore, I am just trying to what you are saying is correct, that you have to calculate the height from the h1 from the root to the leaf. Obviously, because I don't have the address to the leaf node. But what I mean to say, if you are going to calculate for this one, let us calculate for this one. I'll calculate from here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this is the 10. Now, if I calculate for all the height, here the height is 3, here it is 7, here it is 10, and here it is 9. The maximum is 10. Therefore, the height of this tree is 10. It means that if I want to add any node in this tree, the maximum times I require to search is equal to 10. And the minimum time in this case will be 3. Because I might insert a node at this place. I will compare with this. I will compare one comparison here, second comparison here, and third comparison here. But that is a chance because the minimum can be 3 or it could be maximum could be 10. That means if I get an element which can be inserted after 3 times, okay, fine. For example, I have a tree like this. Suppose I take 100, say 50, 120, 110, 125, 123, 130, 140. Fine. This is a perfect binary search tree. Now I want to add 20. You will add here. You compare from here. You compare like this. Okay. Compare less than 100. 30. We'll put 30 over here. You require to compare only 2 times. Once with 100 and second with 50. If I want to add 150, I'll compare with this. Then I'll come here. Again I'll come here. Again here. Again here. And add here. I require to compare 5 times. Once with 100, second with 120, then with 125, then 130, then 140, 5 times. Now, since the height of the tree was 5, I required 5 comparisons. That means the complexity of the binary search is equal to the height of the tree. The complexity of adding a node in a binary search tree is equal to the height of the tree. And therefore, if the height is equal to h, the complexity of adding a node into it is order of h. Where h is the height of the tree. Where h is the height. That means it will be always, it will be less than or equal to. No, what somebody wrote, less than or equal to the height. No, we don't call the equal less than. Less than, so obviously it will be there, but we are going to take the worst case. Therefore, we say it is order of h. Less than can always be there. But when we talk about the big O notation always considers the worst case. When I talk the big O of h means it is always h or less than h. But when we are going to write big O, it is always depicts the worst case. Therefore, we will not say less than or equal to. We will say it is equal to order of h. Therefore, what I told you in the very early class, because if I want to go from this place to some other place, you will say that I will take 5 hours to go, maximum 5 hours. That is the worst case. That you have to go from this place to that place, you require 5 hours, maximum 5 hours. That means the worst case is 5 hours. You might reach in 4 hours, you might reach in 3 hours, but you will not. It will always be at least maximum is 5 hours. It cannot exceed 5 hours in any case. Okay, that means this is the concept that the worst case. Now let us take the problems that suppose I am having these elements which I am having. Suppose I want to insert the numbers, say 5, 8, 12, 15, 14, 25, 40. All these numbers are there. And I want to make a binary search tree from these numbers. Obviously, you will make 5 at the root. Then you compare 8. Obviously, 8 is bigger. It will come here. Again, you compare with 12. Compare with 5, bigger. 8, bigger than, you put 12 like this. Again, you compare with here. Say 15, again bigger than 12, will come here. Again you compare 14, again you compare with 5, bigger than 5, bigger than 8, bigger than 12, smaller than 15, therefore you come here. Let's put 18, then 25, then 40. Now by this method, all these 7 numbers will be stored like this. And this is the binary search tree. This is the binary search tree. Okay. Now I've constructed a binary search tree with these 7 numbers. Now I want to add one more number, and I want to add a number that, suppose, say 35. I again compare with 5, compare with this, keep on comparing, and I put 35 over here. How many times I required to search? Obviously 7 times. If I have done it using a linear search, how much time would I have taken? If I use a simple array based mechanism, and suppose this array would have been like this, and if I would have put a 35 somewhere over here, I would have put, I want to search a number over here, it would have taken that much time only. Therefore, the linear search also, it will take that much time in order to do this. The problem is this, when I am implementing over here, since the tree only grows on one side, this is not giving any advantage of a tree. Now, I want the tree to grow on both sides, though not equally, but it should grow on the both sides, because it is just like a linear type. And this type of tree is called a skew tree. A skew tree is a tree where every node will have exactly one child, except the leaf. It will have exactly one child. Every node will have exactly one child, except the leaf, and there will be only one leaf, and there will be only one leaf. And there will be only one leaf. For example, it could be somewhere like this. This again is skew tree. The problem is that if you are going to search in such type of tree, it will take the time equal to the linear search. It will take a time of a linear search, and therefore the advantage of tree will not be exploited. Otherwise, with this one, if I would have had a tree like this, for example, if I would have tree like this, Okay, let us take this tree with these 7 numbers. Now, these two are also tree but not equivalent, because this contains 7 numbers, that also contains 7 numbers. But here the height of the tree, the height is equal to 7. Now here the height is equal to 4. Because the arrangement of the nodes are such that it does not become a skew, but the order of elements which are coming will dictate what will be the shape of the tree. If the number would have come 5, 8, 12, 15, 18, 25, 40, you cannot make this type of tree. You cannot make this type. You cannot make this type of tree. Whereas if the number would have come like 18, 8, 40, 5, 15, 25, 12, the tree shape would have been here. Now the elements what would have come over here will be something like this. Would have come like this. So if I take it will come 18, then 8, 40, 5, 15, 25, and 12. If you make with this number, you will get a tree like this. Whereas with the numbers which are with these numbers, you are getting a tree like this. Therefore, the order of numbers which are coming will dictate the shape of the tree. Now you cannot, the problem with a binary search tree is that if the tree becomes askew, the time to search it in a tree is same as a linear search. Now let us try to understand this one. Why I am going to say like this. Okay. Now you try to search a number, say if I want to search a number, say 15. If I want to search a 15 number in this tree. I want to search a number, say 15. In this one, you require 1 time, 2 times, and 3 times. You will require 3 times. Here you require 1 time, 2 times, 3 times, and 4 times. Okay, fine. In the left hand side, will take 3 times. The right hand side will take 4 times. Not much difference. Now let us take another one. I want to search a number as say 40. Here you will take 1 times and 2 times. That's all. Here it will take 1 time, 2, 3, 4, 5, 6, and 7 times. Here it will take 7 times. Here it will just take 2 times. And there is significant difference between 2 and 7. It means that if a tree is skew, it will take order of n. If it is not skew, it will take order of much less than n. But I told you, you cannot dictate the shape of the tree because the numbers which are coming are in this in the order that you cannot make this type of tree. You cannot make this type of tree in that case. And therefore, binary search tree has a disadvantage that if the tree becomes skew, you will end up in having the time complexity for searching equal to linear search. And therefore, what I am going to say for a binary search tree, the time complexity with an order of n, which is same as linear search. And therefore, there is no advantage of a binary search tree over linear search, in this case. Suppose I want to search 50. In the left hand, in the left tree, it will take 1 time, 2 times, 3 times, 4 times. That is equal to this much. And after 4, you can say 50 is not present. Where in the skew tree, it will take 7 times. Now, in the worst case, the tree could have become something like this. Suppose there are n is equal to 100 nodes. In the worst case, the tree will become like this. Where the height will be, height is equal to 1, height is equal to 2. In the best case, now tell me how many, what is the best case, what would be the height of the tree? Okay, tell me, in the best case, what is the height of the tree? See, in the best case, the tree height would be a complete binary tree. That means it will be somewhere like this. Now tell me, height what? Its height 1 will contain 1 node. Height 2 will contain 2 nodes. Height 3 will contain 3. How many nodes? 4 nodes. Height 4 will contain 8 nodes. Now you have to make sure that this formula,
2 power n.
the formula is something like this. What should be the value of this 1, 2, 3 such that this value should be exactly greater than or equal to 100. Now in that case it is so simple. It's a simple GP. So actually अगर तुम 1 करोगे 2, 4, 8, 16, 32 और 64, ये वैल्यू जो है greater than 100 हो जाएगी, है ना? Therefore this is 2 to the power 0, 2 to the power 1, 2 square, 2 square, 2 cube, 2 to the power 4, 2 to the power 5 and 2 to the power 6. That means it is nothing but 2 to the power 4 plus 2 to the power 5 plus 2 to the power 6. That means the height of this tree will be equal to 6. Should be maximum equal to 6. Whereas for this one, the height will be equal to 100. And see the difference. If it is a binary search tree, both are binary search tree. If it is skew tree, the height will be 100. If it's a complete binary tree, the height will be 6. Because with a 6, height 6, you can have how many nodes? These many nodes. If you want to calculate, (127) nodes. Now the formula. Now tell me, what is the formula for finding the number of nodes if a tree is equal to is having say height h? It's correct. It's a log of ये होगा.
Yes, sir.
ये होगा. चलो. If the height is equal to h, what is the maximum number of nodes a tree can have? You have to get a. I'm just trying to confuse you. Actually, you have to get the figure of 127. ये height की कितनी है? 1, 2, 3, 4, 5. Sorry, it's 7. That means with this figure you have to get a value equal to 127. See, होने गया 2 to the power 7 minus 1 कितना होता है? 127. This is 127. That means the maximum number of nodes in a tree with height equal to h is nothing but 2 to the power h minus 1. And this formula is perfectly formula for that. Correct? Any questions? No, I have a meeting at right now, therefore I'll not. Any questions you want to ask?